All right, so welcome back after that brief break. So in part A of this lecture, we talked about structure on the systems, and we talked about structure on the system signals. When we do our block diagram, we talked about U as a vector, the system as a matrix, or the generalization of a matrix, and that maps from a vector to another vector, which we'll call y. That's another vector. And that we have now a vector space of signals equipped with mostly an inner product space, which we'll usually consider, and a system, vector space of systems. You can add two systems together with a norm, so it's a norm space. And we use the induced norm so that that norm would have nice properties of convergence, in particular make it a Banach space. So these are in Hilbert spaces, these vectors, and the matrix or the system itself is in a Banach space. It does not have an inner product. So in this part of the lecture, we're going to extend a further property of matrices, then the notion of a unitary transformation or a coordinate transformation or a similarity transformation, if we like. We're going to extend that notion to systems as well. So a unitary transformation, a coordinate transformation. So unlike in vectors, in normal vector spaces, however, your Euclidean norm vectors, this transformation is going to be rather complicated. So specifically, we're going to talk about frequency domain. And how the Laplace transform is a coordinate transformation, a similarity transformation, if you will, between the time domain of functions which are defined with a temporal variable, functions of time, and a new vector space, a new Hilbert space, in fact, which is the frequency domain. And we're going to get there through the Laplace transform. Right? And we're going to show that that's a unitary transformation between time domain and frequency domain spaces. Right? So I'm going to do this a little bit backwards. So I'm going to first define what the Laplace transform is, and then I'm going to define what spaces it maps. Well, I'll define what the frequency domain is. Right? So the Laplace transform of a signal in time domain, in L2 particularly, because it's not defined unless U is in L2. So the Laplace transform of a signal in L2 is defined by, and this may look familiar, the integral of that function multiplied with, we can call this a test function if we will, parameterized by S, and integrated from 0 to infinity. From 0 to, we can just make this infinity. Right? There's a limit, and that's why we need all the special structure of convergence, a Hilbert space, in order to make sure that limit exists. So we can think of this then as the inner product, right, between U and this test function, U of t e to the st, negative st, that L2 norm inner product, right? So if S then has negative real or positive real part, right? Then this test function is also in L2, and so this inner product makes sense, right? So for any S in what we call the left half, the right half plane, this inner product makes sense, and we can define then this inner product, and this inner product is parameterized by the complex variable S. We'll talk more about the complex variable later. And so obviously there's an infinite number of test functions, right, depending on which choice we use for S. And so then the output of the Laplace transform is that, that sort of parameterized inner product as a function of S, U hat, we'll say. Okay. So that's the Laplace transform. You've seen it before, I'm sure. Laplace transform, you see it somewhere. And of course, we can calculate it for certain functions, which we know, the exponential being the easiest. So basically, this is a projection then of u onto the test function e to the negative st. Right? And it's defined for all values of s. And so that's the map. So this is the map, the Laplace transform. So we'll show that this is in fact a bounded linear map from one vector space, L2, to another vector space, which is H2. And furthermore, we'll show that it's unitary with respect to those norms. And means, of course, basically that it's invertible if it's unitary. It preserves the norms and all of these nice functions. So we're getting a little bit ahead of ourselves, but we can go ahead and, if we're thinking about now the Laplace transform as a system itself, which maps a vector to a vector in different spaces, linear operator from L2 to H2, we can think about it in that sense. Well, then obviously it should have a norm, right? And that's the induced norm from L2 to H2. And we'll show that this is actually 1. Now, if this was class, I would ask people to guess that, but since we're not in class, we're online, I just have to tell you what it is. Right? So I've skipped a couple steps because, of course, what the heck is H2? Right, and so obviously this is a function, but is it in some particular vector space? Where is it? What have we done to this nice time domain function when we put it in terms of a complex variable? Okay. So really, I guess I've gotten ahead of myself. And so I should now then go back and define which vector space it maps to. So when we have our signal u in L2, the Laplace transform is a system which maps now to u hat, which is in H2. Right? So what is H2? It's a signal to a signal, fine, I'm okay with that. But now, what is this space that we've mapped to? And so that, I've put it off because it's hard to, well, it's hard to define, right? It's rather complex in a sense. And so if I put this slide first, the motivation would be sort of lacking. And so it's rather mathematical, abstract, hard to understand. But if you understand what we're trying to do, right, map one Hilbert space to another through the Laplace transform, maybe the motivation makes a little bit more sense. So basically, what is the image of this Laplace transform? So the image of the Laplace transform, when you map an L2 to some other space, H2, well, okay, what do those functions u hat look like? Well, they have certain properties. Relatively hard to define, but we'll do our best. So basically, they are functions which are analytic. They're functions of complex variables, so S is complex. And analytic means something very weird and abstract in complex analysis. So I won't get into the details of what analytic means, basically. But I'll give you a sufficient condition. A function is analytic, right? It's a special math term we use. If, and this is a sufficient condition, it's continuous and bounded, right, as a function of its complex variable. So why would it not be continuous and bounded? Well, remember, actually, in L2, we didn't require our functions to be bounded, only integrable. Here we require it to be continuous and bounded, which basically means when would that not happen? Well, basically, if it's if say it's a rational function, right? It was defined by say p of n of s, numerator over denominator, for example, in transfer function case. Well, if this is a polynomial and the denominator is a polynomial, well, this is continuous and it's bounded if d of s never goes to 0, right? So if the denominator never goes to 0. So if it did go to 0, right, the whole function would go to infinity. Right, so if we think about this is the real part of s, and this is the imaginary part, it's the complex plane. This function has to be continuous and bounded everywhere. Now, H2 only requires us to be continuous and bounded or analytic in the open right half plane. Right. So the open right half plane means when the real part of s is greater than 0. Right. So the imaginary axis doesn't count. We can ignore the imaginary axis, but there cannot be any poles of this function. So there's nowhere that the function goes to infinity anywhere with a real value greater than 0. Right. So it has to be, the function has to be analytic in the right half plane, which seems very abstract. Why are we requiring this? Well, we're not going to get into that, but that's what it is. So we'll just go with it. And for every a function, right, which is continuous and bounded, we can define its limit as it approaches the imaginary axis. Right? This is the limit. So this is the real part of s, and this is the imaginary part of s. Right? So for every fixed imaginary part, we can define the limit as the real part goes to 0 up into the right half plane, because remember it can be discontinuous in the left half plane. That limit exists, and we denote it with u hat of I omega, just letting the real part be 0. So it has to be continuous up until the imaginary axis, not necessarily in the left half plane. We can have poles in the left half plane. And now if it exists, right, that limit, right, and here we'll get rid of this. Just let sigma equal 0 and get rid of the whole thing. Right. So in this case, we want the integral along the imaginary axis to be finite. Right. So we get up to the imaginary axis, and then we integrate along the imaginary axis from negative infinity to infinity, and that entire integral, the frequency on the frequency variable, has to be finite, so less than infinity. So this is has some similarity, of course, and this is where the similarity is most obvious to the L2 norm. This is the H2 norm. It has some similarity to the L2 norm, because remember that was the square integral in the time domain, and so this is similar to that. It's the square integral in the frequency variable. Right. So L2, square integral in the time domain, undergoing the Laplace transform, the square integral in the frequency domain. So integral on the imaginary axis. Right. So now we've replaced sort of our index, like where we're indexing by time, t1 to t infinity, right, with now a frequency, omega 1, omega infinity. Right. So we've created sort of a new parameterization of these functions, but the functions itself don't really change. Right. So we basically created a basis for the functions, L2 functions. Those were, that basis are these test functions. So if you think in vector spaces, remember a vector space is a sum of all of the basis elements. And it's just a projection of your time domain function onto each of those vector those basis functions, right? And so that's what the Laplace transform is. It's a projection onto a new set of basis functions, parameterized by these frequency domain test functions. So we've got now, right, a map from U of t onto, which is maybe parameterized. Say we have L2, which is parameterized by these a basis of test functions, right, I omega t, to now a U hat is a function of a spatial variable, a complex variable, I mean, or a frequency domain variable, which is, how is that parameterized? Well, that we leave to your imagination. In any case, right, the point is that this norm that we're defining satisfies the properties of a norm space, right? So if we have these functions which depend on this frequency domain variable indexed by the frequency domain variable, we can define a norm on that space. That norm is referred to as the H2 norm. So any signal has a finite H2 norm. So don't get that confused with the norm of a transfer function. Transfer functions we have not defined yet. We're talking now about signals in the frequency domain, not systems, not transfer functions yet. Like the L2 norm, we would hope, this H2 norm is also induced by an inner product, right? So if we take these complex valued functions U hat, we take the star, which is essentially the transpose in complex domain. So U hat, essentially the equivalent of U hat transpose V hat. We integrate it over every frequency, and we get that with that 1 over 2 pi here, and that's important because the 2 pi, like the 2 pi has a tendency to come and go depending on actually how you define these things. But we put the 2 pi in as the definition of the inner product. That's where we include it. So clearly, like the inner product of a function with itself, a frequency domain function itself, you recover the norm on that space. Yeah. So we have now time domain vector space, Hilbert space, with inner product square integral of in time, and in frequency domain, the square integral in space. Right? And so we have a map from one vector space to another vector space. Right? And so through the Laplace transform, and so what are the properties of that transformation? So like I said, we want to think of the Laplace transform as a similarity transformation, right? And so in particular, a similarity transform with very nice properties. And in particular, the first property, of course, is that it's bounded. So Laplace transform is bounded. So it's a bounded linear operator from L2 to H2. Now I said that on the previous slide, but I didn't actually state it as a theorem, and it requires proof. And that's what the Paley-Wiener theorem does, is it establishes, in fact, that any element in L2 gets mapped to an element of H2, right? So it's a linear, it maps L2 to H2. And because both of those are well posed, we can, it actually, it has a bound on it. There's a size. This exists. Furthermore, we have some additional properties. So it's one-to-one, and it's onto, basically. So for every element in H2, there exists an element in L2, which maps to that element in H2. Right? So that this space is no smaller than this space. So L2 is not bigger, which is the same thing. Than H2. Right? So this taken together establishes that H2 is precisely the image of the Laplace transform on L2, and furthermore, the one-to-one and onto property establishes that the Laplace transform is invertible, that there exists an inverse Laplace transform. We don't know what it is yet, but these two properties through Taylor-Vierney imply that it exists. Now, we have something else. We have additional properties of this, this invertible transformation. And in particular, the most important property of this invertible transformation, the Laplace transform, is that it is unitary. That is the angle between vectors in the time domain. That's, remember, we had a notion of angles defined by inner product. Going into my picture there. So we had a notion of inner product in the L2 norm, L2 inner product, and the Laplace transform preserves that angle in the frequency domain, right? Because we have a frequency domain inner product as well. So if U gets mapped to U hat and Y gets mapped to Y hat, then the inner product of those two elements in the frequency domain is equal to this identity U in both, of course, right? Because these are the same, times the angle theta, right? So this theta doesn't change from H2 to L2. This tells us, of course, right, in addition, right, it tells us that, of course, the norm of U doesn't change. Under the Laplace transform. Right? So it's an operator which preserves angles. An operator, by implication, preserves norms, and so that tells us, right, that the operator itself is a unitary operator, right? Has the same properties as a unitary matrix. So unitary is defined the same way for operators and matrices. It tells us a little bit more, right? It tells us that these two spaces, because there exists a unitary transformation between the two, are isomorphic. That just means that they have the same structure, that they have the same notion of angle between vectors. So all of those, there's a one-to-one map, and the structure doesn't change, right? So you can think of this then as a rotation matrix. So right. Obviously, the representation of those signals after you've done your rotation is somewhat obscure, but it has the same effect, right? You're mapping from one vector space to another. You're not changing any angles. Essentially, what you're doing is you're rotating, right? That's what unitary operators do. They are rotation matrices. Right? Naturally, of course, we showed that there's an inverse. We would like to define it as well, although we don't use that definition very much. I mean, we're not going to be calculating these inverses at all, but it exists, and you probably actually calculated inverse Laplace transforms in your undergraduate course, right? Again, we're not going to do it very much in this course, but we'd like to know it exists, and if we like, we can calculate it. It's similar to the case for the Laplace transform itself. Here we're taking our function in the frequency domain, and we're taking its inner product now in the frequency domain with test functions in the time domain. All right, so these are e to the st. So these are, again, the same test functions we had for the frequency domain now in the time domain. So they're a basis for the L2. Right. And again, right, we have this issue with real numbers. We can just like make this the imaginary axis for all intents and purposes. Okay. So I omega t. So these are like the half of sinusoids, if you want. So now, again, right, because we have the sigma here because all of these signals have to be finite energy, and technically this doesn't have finite energy, right? So we can only define this for real part of the signals because we require them to decay. So that's why, you know, this the frequency domain is like a little bit, that's why we have all these sigmas. But if you want to think of them just purely along the imaginary axis, that for the most part, that's just fine. So now we can sort of answer this question more rigorously. What is the induced norm of the Laplace transform from u to u hat? Well, obviously, by Paley-Wiener, this is the H2 norm of u hat, which is equal to the L2 norm of u. And so for every test element, this is exactly equal to 1, right? So it's equal to 1. So this thing is equal to 1 for all u in L2, right? So it's an operator or a unitary transformation, similarity transformation with norm 1. Right. So that tells us something, right? It tells us something about the structure of this L2 spores, and it will allow us in later, in fact, in the next slides, to relate input to output signals in the frequency domain much more efficiently than we can in the time domain. Because remember, the time domain, right? If we had u going in, y going out, how do we relate? Well, we had this complex relationship. Y of t is this convolution integral, blah, 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 e to the a t. If we wanted to use our representation, a, b, c, d, to represent that map, we had a convolution t minus tau, b, c, d tau, or something like that. It's a convolution integral, right? Which is very complex, right? It's very hard to represent that easily. In the frequency domain, however, we'll find out that those transfer functions allow us to represent this relationship much more easily in the frequency domain. Right. But okay, so I'm getting ahead of myself a little bit. That's this bit. I should first of all, right, give this some intuition into what these signals look like, right? So in the frequency domain, as you would expect, right, the frequency domain decomposes this time domain signal into sinusoids, essentially. Not really sinusoids because we require them to decay, but sinusoids, if you want to think about them in terms of sinusoidal components, right? So if we have an L2 function that looks like this, it's moving very fast, well, then it's going to have lots of high-frequency sinusoidal components. Likewise, if a signal moves very slowly like this, right, it'll have lots of low-frequency components, right? So that's sort of what Bode plots do. Well, Bode plots are technically applied to the transfer function, but we can also use them to interpret the signals themselves, as in these are the components of the time domain signal in terms of frequency. So if we look at say the H2 norm, right, again, right, it's the integral then of all of those frequency components integrated together. Right? Now we'll talk more about the H-infinity norm starting now. The H-infinity norm is something different. It's also a signal norm, but it's not the square integral of those frequency components. And the H-infinity norm is defined for any frequency domain function, or it's defined in the frequency domain. But it's not the integral. Okay, so H2 was the integral of the frequency domain components. The H-infinity norm, in similar respects to the L-infinity norm, although they're completely unrelated, there's no unitary transformation from L-infinity to H-infinity. But the norm itself is defined in a similar manner. Right? So if you have a complex function, signal in this case, this is a signal norm, which maps the complex plane to, in this case, we have matrices. Here's the function defined on the imaginary axis. Right? The H-infinity norm is just the maximum value that that function takes on the imaginary axis. Right? So it's the maximum norm of that signal, and here we've used, because we're allowing G to be a matrix, we're using the singular value norm. So it's a maximum of the maximum singular value of that matrix along the imaginary axis. And we're deliberately doing this for matrices because we're going to be talking about the H-infinity norm of systems. And that's a little bit of a misnomer because, remember, this is a signal space norm, but the transfer function of a system is actually a signal. Right? So we'll be able to define the norm of the transfer function, and then we'll show that actually that has some relationship to the norm of the system itself. But it's not intuitive at this point that that should be the case. So this is a sort of straightforward definition of the H-infinity norm as the generalization of the L-infinity norm, or the obvious counterpart of it, or obvious frequency domain counterpart. Right. So this signal space, right? H-infinity is a signal space, not a system space, but it has that Banach norm space structure. Right? It's not an inner product, no inner product. Right? But it does have a norm, and under that norm it's a Banach space, just as L-infinity is also a Banach space under the L-infinity norm. Right? So it's a Banach space, it's a normed space, obviously it can't be a Banach space without a norm space, which is defined as the maximum of that signal along the imaginary axis. So if this is a Bode plot of your signal, or your transfer function if you like, the H-infinity norm would then be the maximum of that frequency response, the magnitude response. Remember, there's a phase response, but we're only the magnitude response over the imaginary axis, and this is the imaginary axis, omega. Right. Whereas the H2 norm of that signal was the integral under the magnitude plot of the Bode plot. Right. Likewise, there can be quite a discrepancy between these two norms. Right? So for example, for this signal, right, the H-infinity norm is very large, but the actual integral of that signal is quite small. Right. Counter for the red line, however, right, the H-infinity norm is small, right, but the integral of that signal is quite large, or larger than the other signal at least. Right? So if you think of Bode plots, right, this is the magnitude plot, then there can be quite a discrepancy between these two norms. And so which norm should you be using? How do you interpret the Bode plot? Well, you either look for the peaks or you look for the integral under the curve. Right? So this signal norm, this H infinity signal norm, right? Remember, like, the topic of this course, right? The primary focus of this course is on H infinity optimal control. Right? Right. So are we trying to, does that mean we're trying to optimize the H infinity norm of the output? Right? Well, the output may have finite H infinity norm, or it may not. But it turns out that's not actually what we mean by H infinity optimal control. And so what do we mean then? Well, it turns out we're actually optimizing the H infinity norm of the system. Well, I thought you said, you might ask, I thought you said systems don't have H infinity norms because they're systems and not signals. Right? So where are you going with this? Well, this is where we're going is the idea of a transfer function. Right? So the existence of transfer functions is down here. So, but before I do so, before I get into the existence of transfer functions, let me say that signals can be used to define systems in a certain limited sense. Right? So let me delve into that. So that's this block here, right? So through multiplication operators. So basically, if you have an input, which in the frequency domain, typically, although this can work in the time domain as well, and you have a well, actually, let's just to make life interesting, let's do it in the time domain, and then you have another signal g of t, for example, which is a matrix for all time. Then we can define a map from input to output using that signal g just through multiplication by the matrix itself. Right. So is the system here g? No. That's the important part, right? The system here itself is something else. It is the action of multiplying this function by this function to get this function. And so we differentiate that, and we should try and do this as much as possible. We differentiate the function from its action by writing it this way. We write the system as m sub g. M standing for the action of the system, multiplication by the function g. Right? And so similarly, when we do frequency domain, the action of the function is to multiply the input signal in the frequency domain by the function g to get the output signal y hat, which is g of I omega, or g of s, I should say. U of s, u hat of s. So, technically, I mean, we could do lots of things with any particular matrix valued function. We could do, say, integration or in some way, right? I mean, there are lots of things we could do. Like the Laplace transform is not a multiplication operator. It's an integral operator, right? So we could, right? I mean, we could think of the IST as a transfer function, but then the Laplace transform is not multiplication by that transfer function. Right? So there are lots of things that you can do with a system, signal to create a system. But that's to differentiate between those, we use this particular notation, m sub g hat, to indicate that we're multiplying the input in the frequency domain here by this function g hat. Right? So is this okay? Can we do this? So there's certain results which tell us that if g hat is in h infinity, then we can. So basically, if g hat, and here I'm just not to confuse you, let me erase all this like time domain rubbish. Right? If g hat, that signal, that function, is in h infinity, then if u hat is in h2, then y hat will also be in h2, right? So if g hat is in h2, right, if g hat were to be in h2, that relationship does not necessarily hold. Only works for h infinity. So g hat. Not, if g hat is in h2, the output is not necessarily still in h infinity, or in h2, right? So, but if g hat is in h infinity, we have these very nice results which show that the output is also in h2, right? And that's it's relatively easy to see, right? So look at what m hat g is doing. mg hat u, right? It's taking a function which is analytic, multiplying it by another function which is also analytic because it's in h infinity. And you multiply two bounded continuous functions together, and obviously the output is also going to be bounded and continuous, right? So analytic is preserved under multiplication. So both of these, this one in h2, this one in h infinity, multiplying them pointwise together, right? So at every frequency, results in another function which is also analytic. Furthermore, you can show that the h2 norm of the output is also bounded, right? And how do you do that? Well, it's actually not hard to show, right? It's, remember, the integral over frequency domain d omega. And this term is less than or equal to the maximum value of g over all frequencies times, right, so in this term here is, of course, just the h infinity norm, right? And it turns out this is necessary and sufficient, right? So the output maps from L2 to L2 if and only if the transfer function is h infinity. So right, how restrictive is this? This is a way of representing an action in time domain using the frequency domain. Let's do some erasing here. So what's really going on? Let's take a step back. Right. You have u, which is in the time domain, right? And we have this. We take the Laplace transform of it, and we could take the inverse of Laplace transform of it as well. Right? And then we get the u back. And then what we're really doing is putting that u through g and getting y. And then we do lambda inverse again to get y. In the intermediate step here, we have y hat. In the intermediate step here, we have u hat. And if we draw a box around this concatenation, lambda inverse g lambda, this is mg hat, right? So this is what's going on in the frequency domain. So mapping a frequency domain signal to a frequency domain signal, which we can then back out through the inverse Laplace transform to get back to our time domain signal. Okay. But how restrictive is this? Like, does any system have a transfer function g hat in h infinity such that this whole block can be represented as multiplication by that transfer function? Well, I mean, multiplier operators, I mean, the Laplace transform itself is not a multiplier operator, right? So multiplier operators in general on the frequency domain are much broader than this, right? And so how restrictive is it to only consider operators or systems which multiply by a transfer function? Well, it turned out there's this very powerful result, and of course I won't even take a stab at proving it, but there's a very powerful result said that it's necessary and sufficient. And this is a very surprising result, which says that any causal, linear, time invariant system, I'll replace that with system, for any causal, linear, time invariant system G, there exists a transfer function in h infinity such that this block right here can be represented as multiplication by that transfer function. So that G is lambda inverse multiplication lambda, right? This block, 1, 2, 3. And that's relatively remarkable, right? Yes, that's. I think I shouldn't. Right. That's not actually G, but right. So I should say. Yeah. Okay. Actually, I think no. Actually, I got it all right. So it's lambda times multiplication, composition of the Laplace transform with this multiplication operator, composed with the inverse Laplace transform to get back you to the time domain. Okay, so all good. Right. So this tells us, right, any causal linear time invariant system, there exists a transfer function. That transfer function lies in h infinity, and that part, this block of the diagram, can be represented by that multiplication with that transfer function. Now, of course, this only applies to causal, linear, and time invariant systems. And those are three very important words. Causal, linear, and time invariant. Well, linear we're probably okay with, right? All state space systems are linear. Time invariant, basically, we could define it rigorously, but basically the matrices A, B, C, D don't change with time, right? So if you give the system, if you delayed your input by 10 seconds, you get the same output as the original input, just delayed by 10 seconds, right? So this is your input, this is your output. If you delay, that implies that if this is your input, right, this is your output, right? The output here at time cannot see ahead to figure out what your input's going to be and act in response to that. So that's causality, and then time invariance means that these two cases look the same. Right? So causality means you can't act on things which haven't happened yet, which is relatively basic property of most physical systems. Linearity, which we talked about earlier in terms of linear systems. All state space are linear. And then time invariant just means the system doesn't it's always going to act sort of the same, right? It just sits there and doesn't change. So if you decide to act on it 10 seconds from now, it's not going to change its properties between here now and then. So under that constraint that the system be causal, linear, and time invariant, there always exists a transfer function which allows you to represent that system through multiplication by that transfer function. Right? And so when we talk about H infinity, we usually think the most useful interpretation of H infinity then is that set of transfer functions, right? Because now we've essentially shown that there's a one-to-one map between, right, H infinity and causal linear time invariant systems, right? So in that is invertible, right? So for any causal linear time invariant system, we can define a transfer function, and for any transfer function, we can define a corresponding causal linear time invariant system. Right. Note that this, although we talked about it mostly in the state space context, it's not limited. These results are not limited to state space systems. So state space systems are typically referred to as finite dimensional. However, the results apply to more general classes of systems, infinite dimensional for systems, for example, systems with governed by partial differential equations, systems governed with delay in them, right? These are not representable as state space. And yet, they are still causal, they are still time invariant, typically, and they are still linear. Assuming that they're linear, of course, that's sort of assumption. And so the results of this, they also have transfer functions. Right. So what we've done now is we've sort of shown that we can think of these block diagrams then in both the time domain and the frequency domain, right? G, maybe K, actually, let's put it here. So we can think about them in the time domain as systems with input U and output Y. But we can also represent them in the frequency domain using also our block diagram algebra, because the H infinity, these transfer functions, define an algebra. But unlike sort of the abusive notation we had in undergraduate courses, let's try and be careful and use the notation M sub G to indicate the system and differentiate it from the signal which represents the system, right? And we can plot it like using Bode plots. The magnitude, we can parameterize it using the magnitude and phase plots. And remember, these are complex functions, functions of a complex variable. So we can represent these things as magnitude and phase plots using Bode diagrams, but keep in mind that is thinking of them in terms of signals, and there is some relationship between these Bode plots, right, of the signal of the transfer function and the properties of the system, but only that relationship is only limited. Yeah. And so we'll come back and talk about that. So to sum up, right, part B of the lecture, right, H infinity is a signal space. Right. Also, the signal space of transfer functions. The transfer functions are in a signal space. They're functions, right? Functions. Functions means signals, right? So by even the nomenclature, and it indicates these are functions and not systems. But by Paley-Wiener, right, we know that, and the result on the previous slide, we know that there's a one-to-one relationship between these causal linear time invariant systems and these spaces of transfer functions. Right? So if so G is a causal linear time invariant system if and only if there exists a G hat in H infinity, which can represent that system through the Laplace transform. Okay. Furthermore, using the properties of the unitary nature of the Laplace transform, we can in fact take that system, the signal norm, H infinity signal norm, and tell us something about the properties or the norm of the system itself. Right? So the norm of the system, which is, remember, defined as the sup of GU over U, right? Well, now because this is unitary, right, we can say this is equal to the norm of G hat U hat over U hat, right? Which is the induced norm of this multiplier operator in the H2 space. And as we've shown, right, that induced norm is precisely the signal norm in H infinity of the transfer function itself. Okay. And this sets up the framework for H infinity optimal control, in that what we are going to be doing in H infinity optimal control is minimizing the norm, the system norm of the closed loop system. So we're going to be choosing K, right, such that this map from disturbance to regulated output, right, is the norm of this closed loop system is minimized. So if that's, say, 8, H is overused, say, closed loop, we call that closed loop system. Then we want to minimize the norm of the closed loop system with respect to the L induced norm from input to output, which is, fortunately, the H infinity norm of the transfer function realization there, or maybe I should use CL. Right. So unlike state space representations, the transfer function representation, transfer function is the representation, allows us to relate properties of that representation to properties of the system itself. And that is why we use transfer functions. That is the main reason we are still working in the frequency domain with transfer functions. Now, we will come back to this question because, in fact, in the next part of this lecture, we'll come back to this, because how do we find this, right? Right. Well, obviously, you can plot the Bode plot and analyze the Bode plot, but if you're optimizing, right, how does that fit into an optimization framework? Right? How do you optimize the Bode plot? Well, it used to be that you could do that, right? You sort of like fiddle around with it and see how the Bode plot turns out, or the Nyquist plot, or whatever. But computer algorithms aren't very good at that, right? So actually, we're going to have to turn this back into a system, find the H infinity norm in terms of the ABCDs, right? Which we can then optimize, right? So it's a very convoluted way of looking at the system. We have the system properties, we relate it to transfer function properties, which we can't actually work with, and then we relate those transfer function properties back to our state space representation, and then we optimize on that state space representation. And the key here will be through the KYP lemma, which we'll talk about in the next part. right. So with that, I think this is I'll conclude, yeah, this part B. And when we come back, we'll talk about going back towards the state space representation and using the KYP lemma to relate these two frequency domain and state space representations.